Okay, everybody, so I'm going to try to knock out the rest of Chapter 11, which is going to be the last chapter that's covered in this course. So we should be through all the material today that's going to be on Exam 3 and on the final. That is if you're taking this class in the spring. The summer, things will be a little bit different, and I'll be emailing everybody about that. So for the synthesis of ethers, the thing you gotta recognize here is that probably the most straightforward way, and we've even seen this before all the way back in Chapter 6, is to just do an SN2 reaction. This actually has a name. It's called the Williamson ether synthesis, and all it really is you have a compound that has a good leaving group attached to it, and you treat it with an alkoxy nucleophile, and it undergoes an SN2 reaction. So that is to say, if you have something like this, where you have your compound like an alkyl halide, you treat it with an alkoxide, and it undergoes an SN2 to give you an ether. The problem with this reaction, and this is an issue you need to recognize, is that SN2 reactions are prone to side reactions, particularly with bases, and that they will undergo E2 eliminations if that is a possibility, because an alkoxide is a base as well as a nucleophile, and something I think I said a lot in class is that bases will act like bases first, nucleophiles second, meaning it's a lot faster and easier to extract the hydrogen than it is to get to the backside of a carbon and displace a leaving group. So keep that in the back of your mind when you're doing these reactions. So how do we go about making the alkoxide nucleophile to start with? Because we haven't really talked a lot about that. So the way you do this is you actually can make these from the alcohol itself. You can use a reagent called sodium hydride, or it's even possible to do this with an alkali metal, such as sodium, okay, sodium metal. But let's just say we use sodium hydride. Sodium hydride, which is H-, will extract a hydrogen from the alcohol, and that will result in producing this sodium alkoxide. And since hydrogen H2 is a gas, that leaves, and so that makes this reaction pretty much irreversible. So you have now your alkoxide, which you could then potentially treat with your compound that has a good leaving group on it. And get that to do an SN2 reaction, giving you the corresponding ether. Okay. So if we want to see this in real life, the way we could do this is, let's say we want to make a propyl ether. So we take propanol. What we're going to do is we're going to treat that, one propanol, we're going to treat that with sodium hydride. Okay, that will give me the sodium, that'll give me the sodium salt, sodium alkoxide nucleophile. And if we want to attach a 2-carbon system to that, let's just say we use something like ethyl iodide, okay, that can do SN2 reaction. So you're going to have that and sodium iodide for your inorganic material. And the yield for this is okay, about a 70% yield. And the reason why it's not higher is because of the other thing that can happen here. You have a side reaction. And that side reaction is that you have hydrogens here that are on this beta carbon. So the other thing that can occur is your propoxide attacks that, and this undergoes an E2 reaction, and so you start to see some formation of ethene and a regeneration of your alcohol. Now, of course, this can be controlled a little bit. If you control the sterics here, you can improve the overall yield. Also, heating generally promotes elimination. So you guys remember how to promote an SN2 over an E2. We've talked about that before. Okay. Now, some things that we can do with ethers is well, one of the things you should know is that ethers are very sensitive to they're very sensitive to acids. And what I mean by that is that when you put an ether in the presence of a strong acid like a hydrogen halide acid, what will happen is it will undergo decomposition and give you an alcohol and a corresponding alkyl halide, kind of like the opposite of what we were just doing. And the reason why it does this is because the oxygen in the ether is sensitive to acid. So what happens is when you protonate that oxygen, it becomes an oxonium ion. And now what can happen is that the corresponding X group of your acid, so if this was an HX, well, that is going to be able to come in here and do your decomposition. And there are added problems here. If R and R prime are not equivalent, well, then you're going to see other compounds over here. In other words, it's just as likely that the X minus could have come over here and attacked this R group as well. And so you're going to expect to also see R prime OH and RX as well. So this can be a big mess if you're not careful. This is generally a reaction that you want to avoid happening. And the reason for it, obviously, is you have multiple products here. Now, the reason why I'm mentioning it is because a very common solvent that we see in organic chemistry is tetrahydrofuran. This is THF. This is a very good polar aprotic solvent, and it's used a lot in organic chemistry. So the problem when you put THF in the presence of an acid like HCl is it protonates the oxygen. You end up with an oxonium ion, and then the chloride can come in and attack and open that ring up. Which, if you're wanting this to just act like your solvent and not start doing chemistry on its own, this is what can happen if you put THF in the presence of a strong acid. So this is more kind of a cautionary tale. Now, if we want to talk about some other ways that you can make ethers, there are alternative methods that utilize some chemistry that we've already talked about, such as oxymercuration. Now, everybody should remember this back from chapter 8 when I was talking about this. Oxymercuration can be used to add water into an alkene via a Markovnikov addition. So that is to say that if you have this compound and you were to treat that with this alkene with mercury, and I'm using mercury triflate here, so we talked about the triflates. Those are good leaving groups. This is just a source of mercury +2 in the presence of water, followed by sodium borohydride with hydroxide. If this was going to do a Markovnikov addition of water, you're going to add hydrogen to the side of the double bond that has the most number of hydrogens. So there's a hydrogen right here. There's no hydrogens up there. So that means you would end up adding your hydrogen down here. And your OH there. Okay, and so that's just like what we've talked about back in chapter 8. Now, what would happen if you switched out water with an alcohol like ethanol? Now, in other words, the same set of reagents, but now have ethanol in there instead. Okay, well, if we go through the mechanism again of how this works, so the pi electrons go after that mercury, and you end up forming a merconium ion, like so. The partial positive charge is most stabilized here at this carbon. So this is where we see our delta plus most stabilized. And so the ether, just like, or the alcohol, just like water, is attracted, lone parent oxygen is attracted to that position. And so it opens it up in the same type of manner. And your mercury can now be reduced off with the sodium borohydride and the hydroxide. So the hydroxide will remove that acidic hydrogen. And then the mercury is going to be reduced off with the sodium borohydride, which effectively transfers H minus into that. And the reason why I'm going through this in a little bit more detail now is when we get, if you're taking Organic 2, the very first thing we're going to be talking about in that class is reducing agents. And so we'll get into more detail about how those work in that class. But nevertheless, that is how you could essentially make an ether using oxymercuration, demercuration. Now, just kind of a footnote on this as well, you can do similar chemistry with alkynes in that, if you remember, we said if you take mercury and water with an alkyne, that'll do a Markovnikov addition with the alkyne. It ends up producing an enol, and we said that that enol is going to rearrange into this ketone. This right now, you don't need to worry about how that works. That's going to be something that we're going to talk about in 2342 as well. I just want to mention it here, okay? Now, if you were to do this with the same thing, but with an alcohol, well, you don't produce an enol, okay? You actually produce a vinyl ether, and these are things that can actually be isolated and stored. So you would end up with this this type of vinyl ether. Okay. Now, the next thing I want to talk about, we're getting into probably the most important stuff in this section, which is a discussion of three-membered oxygen heterocycles that are very useful in organic chemistry, called epoxides. Epoxides are obviously a highly strained ring because it's a three-membered ring. They can be selectively opened in acidic or basic conditions, and it turns out that epoxides are fairly easy to make if you have a reactive alkene double bond. So we're going to talk about that first. So the synthesis can be generated from just treating an alkene with an electrophilic source of oxygen, which is often found in organic peroxides. The problem is peroxides are often explosive, and so there has been a more stable reagent that has been developed, which is this guy right here. So that is, this is the structure of MCPBA, stands for metachloropurbenzoic acid. You don't have to worry about how we named that. We'll go into that also in organic 2. But you want to notice that it also has this weak oxygen-oxygen bond here, which allows for us to transfer this oxygen into an alkene. And I'm going to show you how that works right now. Now, MCPBA is a solid, and it can be used and measured out. It's easy to work with. So if you were to just take cyclohexene and you were to treat it with MCPBA, you would make this bicyclic epoxide shown here. And the nice thing about this whole process is this is a concerted one-step mechanism, meaning everything happens at once. So this is the oxygen right here that I've colored in that the pi bond goes after, the pi electrons. And then that allows for this bond to break. And then those electrons on the pi bond here in the carbonyl to go after the hydrogen. And then those electrons to wrap back around and attack the other side of that compound, giving you this syn addition epoxide. And notice I have it drawn in the same direction. Now, since this is symmetrical, I don't have to worry about different enantiomers, but if it was not symmetrical, you would need to consider other stereoisomers that may be present. Okay. Now, the things that we can do with epoxides is epoxides can undergo ring opening. That is, the nucleophile attacks the more substituted carbon when you are reacting an epoxide in the presence of acid. So for instance, if I had this epoxide and I treated it with acid in the presence of methanol, the first thing that's going to happen is you're going to protonate the oxygen, okay? Now, when you do this, the carbon that is more substituted is where the partial positive charge is the most stabilized, okay? And so that is where the incoming lone electron pair on methanol is attracted to that. So this oxygen attacks that position, and then the electrons go on to the oxygen, opening that ring up. So you now have an OH up here. I'm going to draw this so that you can see it. There's your methanol that's added in. That still has a positive formal charge. And we call it a catalyst for a reason, because this guy right here can come off in the solvent. So if this was a little bit of aqueous acid, then we will have some water in here that could facilitate that. And now I'm going to try to draw this out pretty. So I've got an OH, 2 carbon, so it's carbon 1, carbon 2. So that's carbon 1, carbon 2. Then I've got a methyl group there, and then an O, and then a CH3. Okay, so that gives you this, this ether, okay, when you do this. Now, if you took the same reagent, okay, but you treated this in basic conditions, meaning you don't have acidic hydrogens in there. And again, what I mean by basic conditions is that you have basically your alkoxide present without any acid. And so you're not using an alcohol, you're using an alkoxide to open this up. Well, then it's going to attack the least substituted carbon because it's going to be doing a straight SN2 reaction, okay? And so that means that the oxygen lone pair is going to want to go after the least sterically hindered face. the least sterically hindered face. So that means it's going to open it up and do a straight SN2 reaction, okay? Now I'm going to try to draw that out, what just happened. So I now have a bond between the oxygen and that methoxide, and the oxygen now has a negative formal charge, and I have my methyl group there. So now you can see here that I'm going to neutralize everything in acid in a second step. But before I do that, I want to explain why this is called base catalyzed. So the methanol that's also present in here will act as a proton source initially. And so that regenerates your methoxide, which can go and do this again. Just like up here, you regenerate your acid in the last step, which can go and assist in the ring opening up there. Now, the reason why we have to acidify everything in a second step is obviously you want to neutralize that base up there. So that will neutralize that to methanol. It'll get protonated. But now if we draw out our product, you're going to see the product here is a little bit different than the one that we saw before. Okay, so this is now the ether that we are producing. And notice that it has a different, is a completely different product than the one from before. So this is the real attractive feature of epoxides, is it gives you a lot of control as far as the regiochemistry is concerned as to where and how you want to open them. And because they're highly reactive, it makes it easy to install nucleophiles into those positions. You could use alkoxide bases, but you could use other nucleophiles as well and ring open them up, and even form carbon-carbon bonds if you start thinking about using those sodium alkanides that we were using in Chapter 7. Okay, so I'm not going to keep droning on. That is pretty much all of the material for the course. I will probably do a review video coming up in the next couple of days, but I wanted to get all of this material out now so you'd have the weekend to study and get your homework knocked out. So I hope everybody is doing okay, and if you have any questions, post them in the comment section, and I will speak to you again soon. Take care, and bye-bye.